Hello everyone, welcome back to the Regents Chemistry Review series. In this video, we are going to talk about chemical bonding. So, chemical bonds are defined as the attractive forces between atoms or ions in a compound, and valence electrons are what's kind of the foundation of bonding. So, they're responsible for the chemical properties of the atoms. So, just a quick reminder, your valence electrons are the electrons in the outermost shell, and these are also the electrons with the most amount of energy because they are the farthest from the nucleus. So, if electrons are gained or lost, that means atom is trying to become stable and it's trying to have a complete octet. So, when that happens, after electrons, let's say, become ions or whatever they're doing with their electrons, whether they are transferring them to something else, whether they're sharing them, that kind of dictates the type of bonds that they are making. But the overall reason for why something is happening to the electrons is because they are trying to have a complete octet and to become stable. So octet rule, very quick reminder, is when compounds want to have a noble gas configuration, meaning 8 electrons in their outermost shell. So another very quick thing that we want to remember, or that's super important about chemical bonding, is the Lewis dot diagram. So this type of diagram represents the number of valence electrons in an atom. So the general rule for writing the Lewis dot diagram is that we can have a maximum of 2 electrons on each side of the symbol of the element, and then we can have a maximum of 8 electrons around the symbol. So overall it looks like this. When you are trying to fill your electrons around the symbol of the element, remember that you want to put 2 electrons on the top first, and then you want to go kind of clockwise. So it's going to be 3rd, 4th, 5th, and then 6th, 7th, 8th. Okay, so make sure that you remember this quick order to draw your Lewis dot diagram. So let's look at few very quick examples. So if I ask you to draw the Lewis dot diagram of cobalt and chlorines, for cobalt, it's going to look like if you look at your periodic table, you'll notice that cobalt has 2 valence electrons only, so that's going to be 2 electrons at the top because 1 and 2 are supposed to go at the top. And then for chlorine, it has 7 valence electrons, so you're going to have 2 valence electrons at the top, and then we have 3rd, 4th, 5th, then we come back for the 6th, and then the 7th. So here's your Lewis dot diagram for chlorine. So let's talk about the first type of bonds, which is the ionic bonds. So ionic bonds are formed between a metal and a non-metal, and they are formed by the transfer of electrons. So remember that metals tend to lose electrons and non-metals tend to gain electrons. So the electrons are transferred from the metal to the non-metal, and that's how they bond with each other. So they are transferred to achieve the noble gas configuration. We have the anions, your non-metals, as we just said, and we have the cations, which are your metals, and because they have the opposite charges, they attract each other, and they result in what we call the ionic compound. So let's look at a quick example of the electron transfer and how we draw the Lewis dot diagrams for ionic compounds. So let's say we are trying to see how calcium and phosphorus atoms are going to transfer their electrons. So calcium has 2 valence electrons, so that's going to be 2 electrons over there, and phosphate has 5, or phosphorus has 5 valence electrons. So 1, 2, 3, 4, 5. Now, what's going to happen is that calcium can transfer both of its electrons to the phosphorus, so we can have 1 electron there, we can have another electron here. Now the problem is phosphorus still needs 1 more electron. So what we can do in this case is that we can go ahead and bring in another calcium atom. So here we have another calcium atom. Okay, so now this calcium atom is going to transfer another electron to the phosphorus. Now the problem is that we still have 1 electron left on the calcium, so now this calcium is not stable. So we're going to have to go ahead and bring in another phosphorus. So here's another phosphorus with 1, 2, 3, 4, 5 electrons. So this one electron can go to this phosphorus. Now the phosphorus still has 2 more electrons left, making the phosphorus unstable. So now we can bring in another calcium, so Ca, with 2 electrons, and then these 2 electrons are going to go to this phosphorus. So overall, what's happening in this case is that we are using 3 calciums and we are using 2 phosphates. If I ask you to write the Lewis dot diagrams of the calcium ion and the phosphate ion, remember that calcium ion is losing 2 of its electrons, so that's going to be calcium with a charge of +2. And then actually let's try to write the, let me get rid of this. So let's try to write the Lewis dot diagram of like the whole thing. So we have calcium with a charge of +2. And then we have phosphorus, and we know that each phosphorus is gaining the 3 electrons. So we are also going to include the full octet for the phosphorus, and then we're going to include the charge for the phosphorus. So the quick rule to remember here is that for your cation, we do not include the dots, we only include the charge. And then for the anion, we do include the 8 dots with the charge. So now something else that we want to include in this Lewis dot diagram, other than both of our charges, is that how many of each ion are we creating, or how many atoms of each thing are we using. So for calcium, because we have 3 atoms, we are making 3 ions, we are going to represent that, but that 3 with a coefficient next to the calcium. And then for phosphorus, we are using 2 of them, so we are going to put that as a coefficient next to the phosphorus. Please remember that this 2 has to be outside the bracket. Please do not put the 2 inside the bracket. Okay, that's a general rule for writing this. So for your ionic compounds, the thing to remember is that we have, when we are writing their chemical formula, we have a coefficient that represents the number of moles of each substance, and we also have the subscript that represents the number of moles of the preceding element. So they have to be electrically neutral. Here's what I mean by that. If you look at your calcium and phosphorus, we have 3 calciums that have a charge of +2. And then we have 2 phosphorus that have a charge of -3. I'm kind of not writing the, actually I should write the dots for now, just so you all don't get confused. Alright, so here's my phosphorus, okay? Now, if you add these charges, for calcium, we get 3 times +2, you get +6. And then for phosphorus, we get 2 times -3, you get -6. So overall, your charge is 0. Okay, so that's what we mean by electrically neutral. Ionic compounds are electrically neutral. Their charges must add up to 0. And then when we are trying to write their chemical formula, it's going to look something like this. Because we have 3 calciums, so I'm going to write 3 calciums, and I use the subscript of 3 to represent that I have 3 calciums. And then we have 2 phosphorus, so I'm going to use the subscript of 2 to represent that we have 2 phosphorus. And here is your chemical formula for this compound. Okay, so let's think about if we have a shortcut for writing this formula. So that's what we're going to talk about in the next slide. But just one quick definition that I want to introduce before we talk about the shortcut is the word binary ionic compound. Whenever you hear the word binary ionic compound, that means that we have an ionic compound that has 2 atoms only. Okay, so ionic compound that only has 2 atoms. So let's talk about the shortcut for determining the chemical formula and the Lewis dot structure for ionic compounds. So all you have to do, if I ask you to write an ionic compound between calcium and phosphorus, instead of doing all of those arrows and like moving the electrons and all of that stuff, what you can do is something that we call the crisscross method. So you go ahead and write the ions with the charges of both of your elements. So we have calcium and phosphorus. So we write their ions. And then you're going to do the crisscross. So bring their charges down. So you're going to bring the 2 from the calcium down to phosphorus. And we're going to bring the 3 from the phosphorus down to calcium. So that is going to give us this chemical formula. So calcium is going to have a subscript of 3 because we are bringing that 3 from the top. And phosphorus is going to have a subscript of 2 because we are bringing the 2 from calcium. So using this, you can go ahead and write your Lewis dot diagram, because now you know that you have 3 calcium, so you use the 3 as a coefficient and you write the ion of calcium, and then you know that you have 2 phosphorus, so you write the coefficient of 2 and then you write phosphorus with its charge. Alright, so this is like your shortcut for writing the chemical formula and the Lewis structure for the ionic compounds. The very, very important thing to remember about ionic compounds is that whenever you're writing the chemical formula, you always write your positive ion first, followed by the negative ion. Please do not try to write the negative ion first. Alright, let's talk about some rules for naming the ionic compounds. The first thing that you have to do is identify the name of the, identify your metal and then just name your metal. So in this case, our metal is calcium. Okay, so it's going to be named as calcium. And then we are going to name the nonmetal. However, so in this case, our nonmetal is phosphorus, but instead of saying calcium phosphorus, we are going to replace the suffix, we are going to add the suffix "ide" with the nonmetal. So it's going to be phosphide instead of phosphorus. So that will be calcium phosphide. All right. Now, sometimes what can happen is our metal can have more than one possible charges. We also use the word oxidation state for that. So this normally happens whenever we have what we call the transition metals. So here's an example of that. We have copper chloride. Let's say we want to go ahead and name this, but then we figure out that copper is a transition metal. So copper can have 2 possible charges. So when we name this, we it's not just going to be copper chloride, it's going to be something else. So here is the rule for naming any ionic compounds that have a transition metal. We want to figure out what charge is copper using out of +1 and +2. Okay, so we are going to identify and name the metal, but because it has more than one charges, we want to write the specific charge that it is using, using the Roman numeral. Okay, so that charge will be determined using what we call the anti-crisscross method. And then we can just name the nonmetal with the suffix "ide." So let's try to do the anti-crisscross method to figure out the charge of copper chloride in this case. So anti-crisscross is the opposite of crisscross. So that means instead of coming from top to bottom, we're going to go from bottom to top. So in this case, we're going to bring the subscript of copper to the top. So it becomes the charge of chloride. And then we're going to take the subscript of chloride to the top. So it becomes the charge of copper. So by doing that, copper gets a charge of +2 and chloride gets a charge of -1. So when we name this compound, we're going to say copper, and then the charge of copper is 2, so the Roman numeral for that is going to be just 2 I's, and then chloride for your nonmetal. Alright, so this is how we name any ionic compounds that have a transition metal. Now sometimes we can also have non-binary ionic compounds, meaning any ionic compounds that have more than 2 atoms. So examples of those are the ionic compounds that have polyatomic ions. So very quick definitions, your polyatomic ions are charged species because they are ions, right? So they are charged species that have 2 or more atoms covalently bonded with each other. You are given a bunch of polyatomic ions. These are pretty much all of the polyatomic ions that you need to know of. They are given to you in table E. So please make sure you know where to find them. And then very important thing to remember is that if we are looking at ionic compounds that have polyatomic ions, then those compounds basically have both type of bonding. They have ionic bonding and they have covalent bonding. And that's because the atoms that we have in the polyatomic ion, as we mentioned earlier in the definition, those atoms are covalently bonded to each other. But then you take your polyatomic ion and you combine that with the other ion and you make an ionic bond. Okay, so sometimes what can happen is that they can give you a multiple choice with 4 options and they'll say which compound has both ionic and covalent bonding. So your answer is going to be the option that has a polyatomic ion. So you're going to have to use table E to answer that question. Okay, so how do we name these compounds? Any compounds that have polyatomic ions? We're going to name the polyatomic ions using table E, so that means you do not have to memorize all of these names. And remember that your polyatomic ion could be the cation or the anion, meaning it can either have the positive charge or the negative charge, so we're going to have to name accordingly. So if your polyatomic ion is, let's say, an anion, you are going to name your cation just like we were naming them in your binary compounds. So you have to pay attention to the charge of the metal. So if the metal only has 1 charge, no Roman numeral. If it has more than 1 charges, you're gonna have to figure out the exact charge and then make sure to put the Roman numeral. So here's an example. We have NaOH. So sodium only has 1 charge. So that's going to be just sodium, and then OH, if you look at table E, is going to be hydroxide. So that is sodium hydroxide. Then we have iron nitrate. Now iron can have more than 1 charges. So in this case, you're going to have to do the anti-crisscross. So when you do that, iron gets a charge of +3. Nitrate gets a charge of -1. So when you name this, you're going to have to write iron 3, and then nitrate comes from table E. If your polyatomic ion is a cation, then you just name that first, and then you name your anion ending with an ite. So for example, this one, NH4 is ammonium, and then F is fluorine, which must become fluoride. And sometimes you can also have a compound that has a polyatomic cation and a polyatomic anion. So in that case, you're just going to use your table E to name both of them. So NH4 in this case will be ammonium, and OH is hydroxide. So that is ammonium hydroxide. All right. So some properties of ionic compounds that we should be aware of. Ionic compounds are crystalline solids, meaning they do have somewhat of a 3-dimensional arrangement of the ions in their solid crystalline structure. They're also very strongly bonded, so that makes their structure very rigid and stable. And because of that, ionic compounds have very, very high melting and boiling points because their structure is so stable and so rigid. So they in terms of the conductivity, remember, very quick reminders, when we are saying that something is a good conductor, that means this thing has the capacity to allow the movement of charges, because electricity is the movement of charges. So when ionic compounds are in the solid phase, as we just said, they have very stable rigid structures, so the ions do not move. So in the solid phase, they are insulators because no movement of ions. However, when they are melted or when they are dissolved in water, in both of those cases, they can conduct electricity, because in that case, the ions can move freely. We are going to talk more about the aqueous solutions in a bit, but just remember that when we dissolve something in water, the ions break apart. And so now that the ions are moving, there will be more conductivity. All right, let's talk about the metallic bonds. So metallic bonds are the attractive forces between metals. So for metals, very quick reminders, as we have said earlier, metals tend to lose their valence electrons very, very easily. So they result in cations, and then whatever electrons they have lost, um, they form something called a sea of electrons, which looks something like this. So we have those free electrons in between the cations. So your metallic bonds consist of the attractions between those free floating electrons and the positively charged cations. Okay, so those form the metallic bonds, and it's very important to remember that the sea of electrons that you see, that is kind of stopping the cations from repelling each other, because remember, in chemistry, same charges repel, they do not want to be together. So that the sea of electrons is stopping those positive charges from repelling each other. So some properties of metallic compounds that we should be familiar with. One, remember that metals conduct electricity, and the reason why it is possible for them to conduct electricity is because they're we do have the charged particles that can move freely. So we have the cations and we have the sea of electrons that are constantly moving. So that's why the electricity can be conducted. They are malleable and ductile, meaning we can shape them in different ways. And that is because the sea of electrons that you see there, if you apply force, the sea of electrons makes it possible for the cations to kind of slide on top of each other and just like move around. So this is what makes the metals malleable and ductile. All right, let's talk about the covalent bonds now. Covalent bonds are the attractions between different non-metals, and this happens when they share the electrons. So let's talk about the Lewis dot diagrams of covalent compounds. So here we have some examples. Let's talk about the steps first, and then we're going to go ahead and draw them together. So the first thing that we want to do when we are making the Lewis dot diagrams of covalent compounds is determine the central atom. So that is normally going to be the atom that needs the most number of bonds. And then we are going to okay, well, okay, so then we're going to pair the electrons so that they are shared, and remember that we want to have a complete octet for each atom. If we do not have enough electrons, then we're going to make a double or triple bond that we're going to talk about in just a little bit. And then we are going to count the electrons on all of the atoms and just make sure that we have a complete octet for everything. We want to make sure that we include the lone pairs and also count them towards the complete octet. So let's look at these examples. We have Cl2. So for Cl2, there's going to be no central atom because both atoms are the same. So remember that both chlorines have 7 valence electrons. The reason why I am making the Lewis dot diagram like this, where for the first chlorine I made this electron over here instead of on the other side, is because I want these two to be shared. Okay, so now remember that a single bond represents 2 electrons that are being shared. So now if I want to count the number of electrons for each chlorine, for this first chlorine, we are going to have 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. So this one has a complete octet. If you want to look at chlorine number 2, that is going to have 1, 2, 3, 4, 5, 6, 7, 8. So that is also going to have 8 electrons. So the electrons that are shared, we count them for both of the elements. Okay, so this is your single electrons. We have a single bond here. Remember, single bond is the weakest out of all of the bonds. This is where we are sharing 2 electrons, 1 pair of electrons. Let's look at the next one, N2. We have 2 nitrogens. So remember that for 1 nitrogen, we have 1, 2, 3, 4, 5 valence electrons, and 1, 2, 3, 4, 5 for the other one. So in this case, each nitrogen has 5 valence electrons. It needs 3 more bonds. It can make 3 more bonds to have a complete octet. So That means these two nitrogens are going to make 3 bonds with each other. So the first one is going to be when they share these electrons. The second is when they share these electrons. The third is when they share these electrons, right? So in the neater form, it's going to look like this. And remember that we do not want to forget these lone pairs, which are also called the non-bonding pairs, because they are going to be counted for the complete octet. So now if you want to look at this first nitrogen, it has the 2 electrons in the lone pair and then 6 electrons in the 3 bonds. So that's going to add up to 8. Same thing for the other nitrogen, 8 valence electrons. Okay, so these are forming what we call a triple bond. So sometimes we can form the double or the triple bond, so make sure that you can differentiate between them. In case of a double bond, we are sharing 4 electrons and we have 2 pairs of electrons. In a triple bond, we are sharing 6 electrons and we have 3 pairs of electrons. Now let's look at NH3. This is where we have 1 nitrogen atom. So remember that nitrogen has 5 valence electrons, and then we have 3 hydrogens. So each hydrogen only has 1 valence electron. That means it can only make 1 bond. Nitrogen, however, can make 3 bonds. So because nitrogen can make the most amount of bonds, we are going to put nitrogen as the central atom, and then we are going to put 1 hydrogen on each side. Okay, so now your nitrogen, which is the central atom, is going to have 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So nitrogen is a complete octet. Hydrogens are not going to have a complete octet. The maximum number of electrons that hydrogens can have is a 2. All right, let's look at H2O now. Oxygen has 6 valence electrons, so it can make, let me just make it here. So 1, 2, 3, 4, 5, 6. So oxygen can make 2 more bonds. And hydrogens, as we said earlier, each hydrogen can only make 1 bond. So oxygen is your central atom. Hydrogens are going to make 1 bond here. And so this is your H2O. So this is how you draw the Lewis diagrams for covalent compounds. Now, we can, a very important thing to remember about the covalent bonds is their polarity. So we can have 2 types of polarity. We can either have the bond polarity, and bond polarity depends on the difference in the electronegativity. So if we are saying that we have a polar covalent bond, then that means the electrons are shared unequally between the 2 atoms, meaning they have different electronegativities. So we have partial charges as a result. So overall, the distribution of the electron sharing looks something like this. We have a partial positive charge to represent the atom that has less electronegativity. So that means this is going to have the less ability to attract the electron. And then we have the partial negative charge to represent the electron with more electronegativity. So this one is going to attract the electron more. So however, if the electron is shared equally by both atoms, then we have what we call a non-polar covalent bond. So this is when you have same or similar or closer to same electronegativity. So normally this happens when you have an identical atom. So there's somewhat of an equal distribution of the electron. So bond polarity depends on the difference in electronegativity. Please pay specific attention to what the question is asking. Is the question asking for the bond polarity, or is the question asking for the molecule polarity? If it's asking for the bond polarity, you look at the difference in electronegativity. If it's asking for the molecule polarity, then we look at the shape or the geometry of the molecule. And what we are looking at is whether we have a symmetric molecule or an asymmetric molecule. Okay, so the first thing that we're going to do is draw the Lewis dot diagram of the molecule, and we are going to identify the symmetry of the molecules. So we are going to try to group together the partial charges or draw the lines of symmetry and see if the partial charges are distributed equally or unequally. And the rule that we follow for this is SNAP, which means if you have a symmetric distribution of the partial charges, then that means we have a non-polar molecule. So S for symmetric and N for non-polar. But if you have an asymmetric distribution of the charges, meaning partial charges are not distributed equally, then we have a polar covalent bond or polar covalent molecule. So let's look at these examples. We are looking at HCl first. So hydrogen is partial positive and chloride is partial negative. So if we try to draw the line of symmetry, so remember the line of symmetry could be this or this. It's a good idea to draw both. So if we draw a line in the center, we are going to see that one side of the molecule is partial positively charged, the other side of the molecule is partial negatively charged. So this represents an asymmetric distribution of partial charges. That means we have a polar molecule. Let's look at carbon dioxide. Carbon is less electronegative, so then carbon is going to have a charge of partial positive. Oxygens are going to be partial negative. Okay, so if we try to draw the line of symmetry, if we draw one in the center, both sides of the molecule look the same. Okay, if we try to group together the charges, once again, we are going to have kind of a similar distribution on both sides. So this thing represents a symmetric distribution of partial charges. So that means we have a non-polar molecule. Now, if we are looking at the H2O, here we have oxygen has a charge of partial negative and hydrogens are partial positive. So if we try to draw the lines of symmetry, we are going to notice that both sides, especially the top and the bottom, they do not look equal. If we try to group together the partial positives and negatives, partial negative is on that side, all of the partial positives are here. So we have two different sides of the molecule. So that represents an asymmetric molecule. That means we have a polar molecule. Okay, so this kind of explains why is this does not explain. We're going to talk about next why is water drawn like this. So because if we go ahead and draw water like this, in that case oxygen is going to be partial negative, hydrogens are going to be partial positive, and we can technically say that, well, we have a symmetric distribution. So why do we not draw water like this, and why do we draw it like this? The reason for that is your molecular geometry. So your symmetry is impacted by the geometry. So that's what we're going to talk about next, that how do we determine the molecular geometry? How do we know how do we want to draw each molecule? So molecular geometry kind of depends on how the bonds and the atoms must be arranged. Remember that all of the bonds and the atoms, when we are drawing the Lewis dot diagrams, have to be at a maximum distance from each other in covalent compounds. So let's talk about the different type of geometries that are possible for covalent compounds. So we can either have a geometry like this. So this is CH4. We see that we have carbon in the middle, 4 hydrogens. These like cones and the dotted lines that you see, they represent that they are in different planes. So this is kind of like a three-dimensional model of the molecule, because remember that they are in the three-dimensional space and they are trying to be as far apart from each other as possible. So this type of geometry is called a tetrahedral. We have a tetrahedral geometry for a molecule whenever we have 4 electron domains. Electron domains means all of the places on the central atom that are occupied by either a bond or a lone pair. Okay, so all of the places on the central atom that are occupied by either a bond or a lone pair. The maximum number of electron domains that we have is 4. So in this case, all 4 electron domains are used and all 4 of them have bonds. There are no lone pairs. So whenever all 4 electron domains have bonds and there are no lone pairs, we have a tetrahedral geometry. If we are looking at something like this, where we still have 4 electron domains. However, three of them are bonds, and one of them is a lone pair. Then we have a trigonal pyramidal geometry. If we are looking at uh, um, if we are looking at geometry like this, where we have only three electron domains and all three of them are bonds, there are no lone pairs. This thing is trigonal planar. Now, a question that you might be asking yourself is that this central atom right here does not have a complete octet. Boron is only, if it has three bonds only and no lone pairs, it only has 6 valence electrons. And that is because boron is an exception to the octet. The reason for that is if you look at boron in your periodic table, boron only has 3 valence electrons. So if we go ahead and kind of rearrange those 3 valence electrons and put them on 3 different sides, the maximum number of bonds that boron can make is only 3. That's it. It doesn't have any more electrons to make any other bonds. So boron is an exception to the octet rule. It is never going to have a complete octet. So it's never going to have 8 electrons in the valence shell. All right. If we have a geometry like this, where you still have 4 electron domains, however, 2 of them are bonds and 2 of them are lone pairs, then that geometry is bent. So this is why water has a bent geometry. And finally, if we are looking at an electron domain like this, a geometry like this, where you have only 2 electron domains and both of them are bonds, then this represents a linear geometry. Sometimes it can also happen, linear can also be something like, let's say, HCl, where you can't necessarily decide which one is your central atom, because like both of them, both hydrogen and chlorine, are only making one bond. But because it looks linear, so if the question asks for the geometry of something like this, the most, or let's say the most probable or closest answer for something like this would be a linear geometry. Okay, so let's talk about the properties of covalent compounds. So remember that covalent compounds are less soluble than ionic compounds, and that's because ionic compounds are very easier to dissociate into ions when they go in the solution. Covalent compounds cannot dissociate into smaller particles, so they are less soluble. They also have lower melting and boiling points compared to ionic compounds, because unlike ionic compounds, they do not have those like rigid solid structures. They also have less conductivity, so compared to ionic compounds. And once again, the reason for that is because electricity is the movement of charged particles. So in this case, there are no charged particles. Covalent compounds do not have charged particles, and it's also very hard for them to dissociate or make any type of particles. So there's going to be no movement of those particles. Okay. All right, next up, let's look at how can we identify, if you're given any compound, how can you identify the type of bond in that compound? Well, first of all, you're going to look at what type of molecule is combining. So if we have a metal and a non-metal combining, we have an ionic bond. If you have 2 metals, we have a metallic bond. If you have 2 non-metals, we have a covalent bond. And if we are asked to identify the type of the compound instead of the bond, then we can look at the electronegativity difference, okay? So if your electronegativity difference is between 0 and 0.5, then we have a non-polar covalent bond, which means we are most likely going to have a non-polar covalent molecule. But if your electronegativity difference is between 0.5 and 1.7, the bond is polar, but the molecule can be polar or non-polar depending on the symmetry. Okay, so the molecule is going to be non-polar if it's symmetrical, and it's going to be polar if it's asymmetrical. And then if your electronegativity difference is higher than 1.7, meaning between 1.7 and 4.0, electronegativity can never be above 4.0. So if it's between 1.7 and 4.0, that means we have an ionic bond, and it's going to be an ionic compound. So just one very, very quick note to remember here is something that we call the ionic character. So if the electronegativity difference, the higher your electronegativity difference is, the higher the ionic character is going to be. Meaning, the more likely that compound is to behave as an ionic substance. And that's because ionic compounds normally have very, very high electronegativity differences. Alrighty, so that wraps up everything about bonding. Good luck. I will see you in the next one.